So I can start. So first I want to thank you so much for the invite. This is the third time I have the great pleasure to share with you some technology insights. What I'm presenting today is the path to the 5G infrastructure and how the LTE will evolve, and especially how 5G will make the difference. Let's start from the LTE, and these slides try to capture the definitions of the different releases and names. So LTE was conceived and launched several years ago, and release 8.9 is basically the baseline. It was then advanced, and the announcement are denoted as release 10 and 12. What I'm going to show you is what is currently coming next. That is called LTE Advanced Pro, which is about releases that has been just frozen or in the process to be frozen. So from release 13 onwards. And now the debate is what is really new here, and how will this current technology mainstream challenge the 5G, or where is the 5G real competitive advantage? If you look at the benefits the new technology brings, I'm talking about the LTE Advanced Pro, you see already that you have a 10 times better performance with respect to the baseline. And if you go a little into the details and analyze what practically we get once the LTE Advanced Pro is deployed, we have several benefits. Benefits not only in terms of bit rate. You see here that the technology will make it possible to aggregate up to 32 carriers, ideally of 20 megahertz each, bringing the speed well above 1 gigabit per second. But this new technology will also allow to enjoy at the same time the cellular connectivity as well as the Wi-Fi connectivity, which are handled together. There are different types of flavors, and it is possible that LTE uses itself the unlicensed spectrum, but LTE can also play in dual connectivity with the Wi-Fi. In addition to this, an important announcement was towards the cellular IoT with narrowband solution, so about 200 kilohertz. And that will allow this technology to serve up to 100,000 connections per cells. In addition to this, the new release will come with massive MIMO, 3D MIMO, and will support a cloud run architecture with plenty of flexibility. An additional announcement is the latency. As you know, this network were designed to deal with our smartphone or cellular phone in general, the infrastructure. So the next step is to allow a device to communicate to another device, but what LTE Pro brings is the capability to make a vehicle communicate to another vehicle, which means has to reduce dramatically the latency, as I said, about 10 times with respect to LTE today, which we need to go down to something around 5 to 10 milliseconds. The benefits tangible we are already having testing in the field are shown on this slide as far as the narrowband LTE is concerned, so that relates to the IoT massive machine type of communications. We have about 20 dB gain power budget, so the coverage is broadly extended. In addition to this, the new model on the device will allow the battery to last up to 10 years with respect to 1 day today. And in addition to this, the costs of the new chipset and the models will go down to $2 to $5. So we are expecting, therefore, technology that will embrace really a massive deployment of things. I want to show you some example of how LTE could really benefit, especially in the device-to-device communication, and I want to show you some results that Nokia attained here in Germany as far as the deployment of mobile edge computing in addition to the cellular connectivity the LTE can provide along the highway. So let's see some of the use cases already well known and published into the spec. So this spec is the ETSI TR of ITS G5, and there are several use cases. I just captured the one I think more interesting. I would like you to pay attention to a particular thing, like you see on this slide. We are talking about using the Wi-Fi connectivity, in this case, to help increase road safety. And these are the four cases analyzed. I will show you what we measure and test here in Germany as far as the emergency electronic brake lights is concerned, so that when this car brakes, it can inform the other cars so that an incident is avoided, so a collision is avoided. And then I will show you how we solve the issue of signaling the other car already in the overtaking lane that I'm in the process of invading the same lane. There are other cases where this type of connectivity is also important, like in the case of emergency vehicle warning, or example where we have an accident in front of us, we can't see it. What we want to show you, I want to show here, is that you see the latency requirements are all around 100 milliseconds. And what we wanted to see is whether we could improve this latency so that this kind of use cases could be broadly deployed with a large degree of safety. If you look at how today the technology works, we have a combination of direct communication between cars, short range, which is supported by a technology called ITS G5, and currently going broadcasted from one car to another car. On top of it, we can deploy a cellular system so that this type of communication can be enriched and enhanced. Now, the target of LTE Advanced Pro will be to replace completely the G5 system, which is truly unreliable for a real type of use cases where the safety is really a matter, so that we can have the communication not only through the cellular system, but using the same type of protocol, we can also make the different vehicle in communication. What was tested in Germany was an interesting use case, and the consortium consisted of about 4 players, so Continental was here, Deutsche Telekom, Fraunhofer, Nokia. The target was, as a co-funded project by the German government, was to test 2 use cases and verify really that the LTE cellular network could provide really a latency below 100 milliseconds with a large degree of reliability. So we tested the cooperative overtaking assistant and the electronic brake light. So what was the target? Is to shift from the current network functionality where you see the complexity. When you make a call from one device to another device, the communication has to go through all network, achieve the switching center, and from the switching center down, find the cell in coverage with that particular vehicle and establish the communication end-to-end. What we want to test now is another solution using mobile edge computing to dramatically reduce the latency between the two peer entities in communication. And that is done using mobile edge computing. Mobile edge computing means, in a high level, that we are going to perform all relevant function done in the core network, say, far away from the radiating element, really on the access point. That's the target. And that's where the mobile edge computing platform is located, and all the radio interface protocol and the non-access stratum protocol are stripped out at this point. So we want to test the benefit of establishing the communication no longer through the core, but simply reversing it at the first access point that provide coverage to the devices. We want to prove that we are on the range of the 20 milliseconds. That was done, and in partnership, as I said before, with Continental, Deutsche Telekom, Fraunhofer Institute, and Nokia provided a mobile edge computing platform, the operator, the infrastructure. Continental focused especially on the application, and the Fraunhofer Institute built up and integrated the onboard unit. If you look at how the system was built, extremely simple. So you have the mobile edge computing platform at the edge, and then on which you have an enhanced protocol stack, through which it was also possible to pass signaling currently exchanged between the two cards now encapsulated to the system, so that it is possible centrally to know exactly what's going on all around the cars that has to be put in communication. Which means the CAN messages as well as the DEM messages are now possible to be elaborated and rendered to the different cards in communication. The onboard unit was very simple. You have a unit which is capable of communicating via cellular, and at the same time is in communication with all relevant devices in the car, and especially the tablet, which is in interaction with the driver. Now, what was tested in the A9 was the performance using 3 access points where the edge computing platform was located. Now, let us see how it worked and the performance results we attained. So that's the case of the electronic brake lights. So you have a car start now braking, and the sensor reports to the onboard unit the signal, the one send it to the cloud, the mobile edge cloud platform, which pass it through cellular coverage to the car following. So then the driver is informed to slow down because the one ahead is start reducing speed. We measured to be below 20 milliseconds using this technology. We also verified that when the car, sorry, there was, wait. That's the other case. I'm sorry. Anyway, so when the car gets really close, you are really informed to slow down, to reduce the speed in order to avoid a collision. Then the other case was to inform the driver already overtaking that I'm now in the process of invading his lane. So what happens is that when the signal is turned on, this information is passed to the edge, and from the edge is broadcast back to the cars in questions, so that both cars and drivers are now informed that something is going to happen, that this is about invading the lane, and this is informed that there is already somebody overtaking. Then, when the speed is reduced for about 40 meters, another message is sent that you are no longer allowed to invade the lane because you happen to be very close to the other car and you have to avoid the collision. The measurements we found was again around 20 millisecond latency, which is well below the expectation you would get if you implemented this system using the G5 technology. So that's the experience of the two drivers. I just replay by just showing what you see when you were in the car. So the first signal, so reduce speed. The second one, okay, now you're not allowed anymore to move left and invade the lane. Okay, that's basically what we are expecting with introduction LTE. Now the question is, where are the 5G benefit? Where this technology will have a truly realistic competitive edge? And the expectations are first that this technology, there are many rumors, millimeter wave, whatever. No. So the first deployment of the 5G is going to be below 6 gigahertz. So we're expecting that coming into the cellular band. Europe, especially China, will enjoy then this technology at 3.5 gigahertz. Only at a later time, the deployment will be in the millimeter wave. If you look at the expected benefit, currently we see that the new technology, which is not just about a new radio technology, we're expecting a completely new system. It should provide the possibility of improving the amount of data that is offered for each cell. If LTE today, LTE Advanced Pro can provide connectivity up to 100,000 sensors or things, here we expect at least 3 times as much. Up to 1 terabyte distributed per square kilometer. Similarly, we want to have a peak rate which goes up to 10 gigahertz, which is 10 times faster expectation of the LTE baseline. Similarly, the latency has to be dramatically reduced, and here we are talking about milliseconds, because the communication has to make it possible, the deployment of machine type of traffic, ultra reliable, with a large degree of, a very little degree of latency. If you look at the number that the new technology will cope with, as I said to you before, we have that the LTE Advanced is around 42 milliseconds. In the best case, we are considering that it will go down around 10 milliseconds, especially for device-to-device communication. And if you look at this graph, most of the performance will be enhanced not only at the radio interface, but also across the whole network, because what has to be reduced dramatically is how the resources are handled and overall the infrastructure delay. And what we expect in 5G really here is to cope with the ultra-reliable latency communication. I want to show you a film taken using the LTE technologies and proving the benefit of 5G using 2 robotic platforms, using a control loop via video camera at the edge. So that means we're not talking about the robot's intelligence per se as an individual, but we are thinking about a robot where the intelligence is close in the network. So let's see whether that works and gives you really a flavor of what I mean here. Now we don't have time, as usual.
4G was really all about communications with people and delivery of video. And with 5G, but I think what we're going to see is a complete transformation where we're talking more about connectivity for machines so that they can transform our lives and deliver services much faster, much quicker than we could ever perceive today. With 4G today, there's higher latency in the network. So this is the amount of time it takes to transmit data from the device to the network and back again. With 5G, that communication path will allow you to communicate much quicker, and you'll be able to control machines. So in this demonstration here today, we have this camera, which is recording the position of this ball on this plate. And then this position is recorded by a mobile edge cloud computing environment that then is intelligently controlling these robots, sending them the commands across the network to balance this ball on the plate.
So the intelligence is not here. Is at the edge.
On the screen here behind
the computer somewhere else connected wireless
would be a 4G
to the robots.
around 90 to 100 milliseconds.
Now it's used first LTE and then switch to the 5G. You see immediately the differences.
So what I'm going to do is move this ball right now, and we can see the oscillations here tracked on this graph and how long it takes for the robots to collaborate with each other to get the information they need to balance the ball on the plate. And then we're going to switch into 5G mode.
So you may think about having this feature in your car, right?
Here that we've gone from around 3 milliseconds.
Now it's going down. Now the 5G system is on air.
We're going to do exactly the same again.
And the communication goes wireless to the robots. You see it
and we can
right
see
away.
that we're into one oscillation there to correct. So you can see how the reduction of the latency
Close loop between the camera here, edge, using 5G, new radio, edge cloud, and then back to the robots, and vice versa.
I think for society, for humanity as a whole, what we're going to see is a transformation of our existing technologies to automate everything. So you can imagine healthcare, automotive, or in the mining industry, or in other areas that are very critical or dangerous for humans. We can actually send a machine in and actually control them remotely over a 5G wireless network because of that low latency in the network. So a huge transformation in the way we utilize our network and what we're able to control and do with our machines.
Okay, I hope you got some insight how the things will work much better, much more reliable with 5G with respect to LTE and the LTE enhancements. Now I would like to go back to the presentation, and the question is how to do that. Okay. Okay, next time I bring the. Right. Okay, great. So here we are. So the mouse is there. Presentation. Thank you. Let's see. Just a couple of slides to go into other details. Okay, great. So let's look at the numbers. We saw latency, and that is a key really enabler. I truly believe if this latency performance can be in place with a large degree of reliability, we have plenty of new use cases, a lot of business coming up. Let's look at the performance. Performance are expected to increase dramatically also in terms of speed, as I presented before. And we have here, you can see that LTE aggregating 5 carriers of 20 megahertz each, which 100 megahertz spectrum may reach ideally up to 1 gigabit per second, or we are expecting 5G to use a chunk of bandwidth spectrum at the same time, much more efficiently, and reach up to 20 gigabit per second. That will be in the millimeter wave, aggregating 2 gigahertz spectrum using 2 times 2 MIMO. If you look at the deployment and the coverage expected in 5G, we are seeing that 5G deployment at 700 should perform as well as an LTE already deployed at 800, which means enjoying up to 100 megabit per second across the cell. We're expecting 5G at 3.5 gigahertz, those are the first deployments, to provide the same experience as the LTE deployed at 1800 and achieve up to 1 gigabit per second. And finally, we're expecting deployment in the millimeter wave spectrum, which is about 20 gigahertz, just to give a number, is up to 10 gigabit per second, with full coverage of 700. As I said before, the capacity of the system will dramatically improve. And at the millimeter wave here, we're expecting up to 1 terabit per second per square kilometer compared to 1 gigabit per second per square kilometer today. How the network will evolve? Just 2 more slides. The network is expected to evolve as shown here. So we do have today an LTE system with an LTE core. The next step will be about to deploy a new radio. And the network will change in a way that the first stage we will have a dual connectivity with LTE, and LTE will be the anchoring point. That means you will need the LTE core to deploy the 5G, and the 5G data plane may come through the interface also used for LTE, or it can be a parallel data path. But the control plane has to be anchored centrally using the LTE core. Then we have the phase 2 of the system coming, which is an overlay system, which is a completely end-to-end infrastructure, where you do have both the signaling and the control plane pass across brand new network, therefore allowing carriers, players to enjoy a 1 millisecond latency, which is not possible if you keep using the same boxes and the old technologies. The core network will evolve also dramatically, and you can see here on the left-hand side of the slide how the network looks like today. Pretty much ossified and still stuck into having a control plane dealing with the user plane within even the same box. That's going to change, and we will have a control plane completely separated from the user plane, introducing plenty of modularity so that my functions dealing with my voice, with my data, has to not interfere with the control plane dealing with the setting up of the communication. Looking at the timelines, and here I would like to conclude, the expectations are the following. That there will be 2 releases of 5G systems. Okay. We have the first phase, as I presented you before, available, standardized at the maximum level of detail on June 2015. This will be followed by another release which will support additional use cases than mobile broadband. Now we are also discussing the standard whether it's going to be even a phase 0, which is about a new radio dealing with the LTE infrastructure itself, achieving simply a dual connectivity and yet another radio. If you look at the Nokia involvement and deployment globally, we are expecting at a high level, say, 2 or 3 main phases. Already next year, we're expecting the deployment of 5G for mobile, for fixed broadband to the home. So it's a fixed wireless access to the home. That's going to happen in the United States with Verizon. So the expectation is to have a 1 gigabit per second to the home and about 5 gigabit per second capacity. Then in 2018, in 2 years about from now, the mobility will be introduced in the system, but as you see in the previous version as well, it will be a pre-standard product. So it's not yet, or at least we don't know, unless this particular standard will become the de facto standard, compatible in theory or a priori with the 3GPP. That will be about the deployment in Korea at the Olympics, which is expected to be in 2018, with full mobility, 10 gigabit per second speed, and achieve already 1 millisecond radio latency. And then later, the commercial product will be 3GPP full compliant, and the first deployment, or one of the first deployments, is expected to be at the Olympics in Japan. And here there will be a full support for extreme throughput, wide area coverage, and especially LTE, dual connectivity, and unlicensed bands will be covered as well. So I think that basically concludes my speech. Apologies for the many interruptions. I hope it is clear are the differences between the evolution of the LTE and the current technology and the advantages we will have when 5G is in place, especially as an overlay system. So if you really want to benefit of these two technology, it's not like when you buy a car that 50% is of 20 years ago enhanced only. In that particular part of the car, what we want to have here in place is the complete overlay flexible system, and therefore we can really enjoy a 1 millisecond latency and speed above 20 gigabit per second. Okay, thank you so much.